What if alien life is just a telescope away? Join us as we explore the weirdest exoplanets in the universe. Have you ever looked up at the night sky, at that vast, dark canvas sprinkled with countless stars, and wondered if we are truly alone? That question, perhaps one of the most profound we can ask, is no longer just the domain of science fiction. It is a driving force in modern astronomy. What if I told you that the answer might be just a telescope away? For millennia, we only knew of the planets in our own cosmic backyard, our solar system. But in just the last few decades, our view has exploded. We have discovered thousands of planets orbiting other stars, worlds we call exoplanets. The sheer number and variety of these distant worlds challenge everything we thought we knew. Today, on this very Halloween of 2025, let us embark on a journey far beyond our familiar blue marble. So, what exactly is an exoplanet? The definition is refreshingly simple. An exoplanet is any planet that orbits a star other than our own sun. For most of human history, these were purely theoretical objects, things we suspected must exist, but had no way to prove. The universe is filled with hundreds of billions of galaxies. Each galaxy contains hundreds of billions of stars. It seemed almost statistically impossible for our sun to be the only star with a planetary family. But seeing is believing, and for a long time, we simply could not see them. They are incredibly small and faint. They are completely overwhelmed by the brilliant glare of the stars they orbit. The game changed in the 1990s. That is when astronomers confirmed the first discovery of planets orbiting a star like our sun. Finding an exoplanet is one of the great technical challenges in modern science. Imagine trying to spot a firefly buzzing around a searchlight from miles away. The planet is tiny and dim, while its star is immensely large and bright. Because of this, most exoplanets are not found by directly taking a picture of them. One of the most successful techniques is called the transit method. We monitor its brightness over time, looking for a tiny periodic dip. This dip happens when a planet passes in front of its star. It is like a mini eclipse. NASA's Kepler Space Telescope was a master of this method. It discovered thousands of potential planets. Another powerful technique is the radial velocity method, sometimes called the wobble method. As the star wobbles, its light shifts toward red or blue. This is the Doppler effect. Our first stop on this tour of weird worlds is a class of planets that completely shattered our early theories of solar system formation, the hot Jupiters. As the name suggests, these are gas giants similar in size to our own Jupiter, but they live in extreme conditions. They orbit their stars on incredibly tight, scorching hot paths, days or even hours per orbit. They are blasted with intense radiation, heating upper atmospheres above 1,000 degrees Celsius, hot enough to melt lead. Large size and strong gravity make them easier to detect via transit and radial velocity. But their existence close in was a shock. Giants should form far out where ice can accumulate. They likely formed far away and migrated inward over millions of years, reshaping their systems. Many are tidally locked, with extreme day-night contrasts and ferocious supersonic winds. Some may even have vaporized rock and exotic mineral clouds. Great labs for extreme atmospheric physics. Next, worlds where it might literally rain diamonds. Now, let's journey to a world that sounds like it was plucked from a fantasy novel. A planet where it might literally rain diamonds. This brings us to a class of exoplanets known as carbon planets, with the most famous example being 55 Cancri A. This planet is a super-Earth, about twice Earth's size and 8 times its mass. It orbits so closely that its surface may reach around 2,400 degrees Celsius, 4,400 degrees Fahrenheit. Its carbon-rich star suggests a carbon-rich planet, graphite crust over a thick diamond layer. Imagine a crystalline treasure trove on a planetary scale, forged by immense pressure. This challenges our idea of terrestrial worlds. Not silicate geology and water, but alien carbon chemistry. Instead of silicate lava, there might be eruptions of carbides and pure carbon flows. An atmosphere thick with carbon monoxide or methane could yield diamond hail into seas of molten tar or oil. While likely hostile to life, diamond worlds show the universe's astonishing chemical toolkit. Next, a planet with no star to call home. Most planets are tethered to a star. But what if a planet had no star to call home? These planetary mass objects roam the galaxy untethered, drifting in perpetual darkness. There could be billions, or even trillions, possibly outnumbering the stars themselves. Two main theories, ejected from a young chaotic system by giant planet interactions or passing stars, or formed alone, like a tiny failed star. Surface, frigid, just above absolute zero. But large rogues may retain internal heat, radioactive decay, and primordial warmth. With a thick hydrogen atmosphere or miles of ice, a subsurface ocean could persist. Where there is liquid water and energy, there is potential for life, powered by chemistry, not sunlight. A self-contained little biosphere, drifting silently through the galaxy. For life as we know it, one ingredient is non-negotiable: liquid water. These exoplanets may be completely covered by a single global ocean. Unlike Earth's balance of land and sea, a water world might have no dry land at all. Oceans could be hundreds or thousands of kilometers deep, likely formed in icy regions, then migrated inward. Surface ice melts into global oceans. Under crushing pressure, water becomes exotic high-pressure ice. Ice 7, Ice 10, solid, even when warm. Result: a liquid ocean sandwiched between vapor or normal ice above and a deep mantle of hot ice below. But if high-pressure ice seals the ocean from rock, mineral nutrients may be scarce. Life might hug the upper layers, using starlight for photosynthesis, or cluster around hydrothermal vents if any connection to the core exists. Finding a water world in the habitable zone and its atmospheric water vapor and biosignatures could hint at life. Despite challenges, vast oceans offer stable, radiation-shielded habitats, prime targets in our search. From the potential cradle of life on a water world, we now travel to one of the most hostile environments: a lava planet. Rocky worlds orbiting perilously close to their stars, some even closer than hot Jupiters. K2-141b is a prime example. Surface roiling with magma, atmosphere of vaporized rock. Precipitation becomes pebble-like rain. True hellscapes of extreme geology, permanently blistering dayside above 3,000 degrees Celsius, nightside freezing. Hot enough to vaporize rock, sodium, silicon monoxide, other crust-forming minerals. Supersonic winds ferry vapor to the cold side, where it condenses and rains. Condensed material returns as vast magma glaciers, a hyper-fast rock cycle of vaporization, precipitation, and flow. Lava planets are not candidates for life, far too hot and volatile, yet invaluable natural labs. They test survival limits near stars and reveal how materials behave at extremes, offering clues to early Earth. After visiting these extreme worlds, the ultimate question remains: could any exoplanet actually harbor life? The habitable zone is where temperatures allow liquid water, our first filter in a vast search. But it's a guideline, not a guarantee. Worlds may be deserts or gas giants. Conversely, habitability may exist outside the zone. Rogue planets, Europa, Enceladus, with subsurface oceans warmed from within. The key is biosignatures, atmospheric chemicals suggestive of biology. On Earth, oxygen and methane coexist only because life replenishes them. When a planet transits, starlight filters through its air. We read chemical fingerprints: H2O, CH4, CO2, O2. With the James Webb Space Telescope and successors, we can sniff trace amounts in distant atmospheres. A convincing set of biosignatures on a rocky habitable zone planet would be one of humanity's greatest discoveries. We stand at a remarkable moment in the human story. After centuries of wondering, we finally have the tools to ask whether we are alone. Giant ground-based telescopes like the Extremely Large Telescope and the Giant Magellan Telescope will gather enough light to directly image Earth-sized planets and analyze their atmospheres in unprecedented detail. Working with space missions, they'll build a complete picture: Closer to home, the Europa Clipper will fly by Jupiter's icy moon dozens of times, confirming its subsurface ocean and searching for habitability. What we learn at Europa will guide our hunt for distant water worlds. This adventure isn't reserved for scientists. You can help via citizen science projects like Planet Hunters, spotting the telltale dips of transiting exoplanets. Your eyes could be the first to spot a new world. Support research, nurture curiosity, share wonder, and never stop asking questions. We do not have proof of alien life yet. We must be honest and rigorous, patient, skeptical, and willing to be wrong. But now we have a realistic path to an answer. Every star could be a sun for another family of planets. Some worlds will be strange, some will be familiar, some might just be right for life. The universe isn't obliged to make sense to us, but it's our privilege to try. So keep looking up. The next great discovery is out there, waiting,